Hello everyone and welcome to the MathDBase.com Anicasts series. I'm your host, John Kisieju. In this installment in the Algebra series, I will discuss Algebraic Techniques, Part 0, Fundamentals of Exponents. Exponential notation is the use of exponents as shorthand in writing large and small numbers. An exponent is usually indicated by a numerical superscript, a symbol written slightly above and to the right of a representative factor called the base. In the expression with a 2 and a smaller 3 written slightly above and to the right of it, pronounced 2 cubed or 2 to the third, 2 is the base and 3 is the exponent. In arithmetic, exponential notation is used to represent repeated multiplication of numbers. The base tells you which number to repeat, and the exponent tells you how many times to write it. So an exponent of 1 means that the base should be written only one time, and an exponent of 3 means that the base should be written 3 times and multiplied. 2 cubed is the same as 2 times 2 times 2, which equals 8. Similarly, 10 to the 4th is equal to 10 times 10 times 10 times 10, and is equal to 10,000. Sometimes the exponent of a number is referred to as its power, so 10 to the 4th might also be called 10 to the 4th power. For the reciprocals of powers of numbers, we use negative exponents. So 1 over 2 to the third is written 2 to the negative 3. But since 1 over 2 to the third is equal to 1/8, 2 to the negative 3 is also equal to 1/8. We will get back to these negative exponents later. In arithmetic, we learn about scientific notation, which is a way of writing very large and very small numbers with powers of 10 in a compact form. For example, in scientific notation, the number 1 trillion, which is a 1 followed by 12 zeros, can be written as 1.0 times 10 to the 12th. Where the exponent of the 10 is equal to the number of zeros in the number, and basically indicating how many decimal places to move to the right after the 1. Also, the number 100,000th, or 0.00001, which is equal to 1 over 100,000, or 1 over 10 to the 5th, is 1.0 times 10 to the negative 5 in scientific notation. In this case, the negative exponent tells you how many decimal places to move to the left of 1. In algebra, which is a generalization of arithmetic, letters are used called variables or unknowns to represent different numbers in different situations. In the expression an x with a 3 as its exponent, called x cubed or x to the third power, x is again called the base, and the 3 is the exponent or the power of x. The 3 indicates that x, or the number that x represents, should be multiplied by itself 3 times. Any expression that has a number, a variable, or a combination of a number and variable raised to some power is called an exponential expression. In algebra, exponents can also be variable or unknown quantities. So the expression x to the nth represents an unknown number x raised to an unknown or unspecified power n. As in the case of an exponent that is a specific number, the exponent indicates the number of times the base is to be written as a factor. So x to the nth means n copies of x multiplied to each other. Here, the exponent n can be any natural number, which are whole numbers larger than 0. Now, let's look at some properties of exponents used to combine and simplify algebraic expressions. To multiply 2 or more exponential expressions that have the same base, use the common base and add their exponents. In symbols, if m and n are natural numbers, x to the nth power times x to the nth power is equal to x to the m plus nth power. For example, given 2 to the third times 2 to the 5th, we have 3 factors of 2 multiplying 5 factors of 2, which is the same as 8 factors of 2, or 2 to the 8th. So 2 to the third times 2 to the 5th is equal to 2 to the 3 plus 5. If you multiply x squared by x to the 4th, you will get x to the 2 plus 4, or x to the 6th. Similarly, if you multiply 2x cubed by 6x to the 4th, the constants 2 and 6 will be multiplied to get 12, and you will have x to the 3 plus 4 to get 12x to the 7th as the result. Now, let's compare that result with this next problem using the same numbers arranged differently. Multiply 2x quantity cubed by 6x quantity to the 4th. 2x quantity cubed is the same as 2x times 2x times 2x, or 2 times 2 times 2 times x cubed, or 8x cubed, where 2x is the base and 3 is the exponent. And 6x quantity to the fourth is the same as 6x multiplied by itself 4 times, or 6 multiplied by itself 4 times, multiplying x to the fourth, which gives us 1,296 times x to the fourth. 6x is the base this time, and 4 is the exponent. The final result is 8x cubed times 1,296x to the fourth, or 8 times 1,296 times x cubed times x to the fourth, or 10,368x to the seventh. So how numbers are grouped can make a big difference in the result. Also, whether the exponent is an even or an odd number can affect the result. Negative 2 to the fourth is not equal to negative 2 quantity to the fourth, though the exponent is the same in both. In the first expression, the base is 2, and in the second, the base is negative 2. Negative 2 to the fourth is the negative of 2 times 2 times 2 times 2, which is the negative of 16. Negative 2 quantity to the fourth is equal to negative 2 times negative 2 times negative 2 times negative 2, which can be rewritten by pairing the negative 2's and then using the rules of multiplication with sign numbers to get 4 times 4, or 16. On the other hand, negative 2 to the third is equal to negative 2 quantity to the third, even though the base in the first expression is 2 and negative 2 in the second. Negative 2 to the third is equal to the negative of 2 times 2 times 2, or negative 8. And negative 2 quantity to the third is equal to negative 2 times negative 2 times negative 2. Two of the negative 2's can be paired and multiplied, then multiplied by the remaining negative 2 to get 4 times negative 2, or negative 8. Another version of the product rule for exponents, sometimes called the power rule for exponents, involves raising powers of numbers and unknowns to other powers. For example, 2 cubed squared is equal to 2 cubed times 2 cubed, or 8 times 8, which is 64. Using the first product rule, 2 cubed times 2 cubed gives us 2 to the 3 plus 3, or 2 to the 6th. But since multiplication is shorthand for repeated addition, we could also write 2 cubed times 2 cubed as 2 to the 3 times 2, or 2 to the 6th. Similarly, 3 to the 4th cubed is the same as 3 to the 4th times 3 to the 4th times 3 to the 4th, or 3 to the 4 plus 4 plus 4, or 3 to the 12th. Since 4 plus 4 plus 4 is equal to 3 times 4, 3 to the 4th cubed is equal to 3 to the 3 times 4. For an algebraic example, x squared to the 4th is equal to x squared times x squared times x squared times x squared, which is the same as x to the 2 plus 2 plus 2 plus 2, or x to the 4 times 2, or x to the 8th. Generally, we can write x to the mth raised to the nth is equal to x to the m times nth, where m and n are any integers. Taking another look at 2x quantity cubed times 6x quantity to the fourth, when we wrote out the problem as the product of its factors and combined, we got 2 cubed times 6 to the fourth times x to the seventh. This problem suggests the following rule called the power of a product. If an exponential expression consists of a base, which is the product of numerical and or algebraic symbols, and that base is raised to a power, the result is the product of each factor in the base raised to that power. Here, a represents any integer and m any positive integer. Since the fraction a over b is equal to a times 1 over b, we can use the power of a product rule to write the power of a quotient, provided that a and b are integers and b is not equal to 0. Applying the power rule to a times 1 over b, a times 1 over b quantity to the mth is equal to a to the mth times 1 over b quantity to the mth. Expanding, we have m factors of a multiplying m factors of 1 over b, which can be rewritten as m factors of a multiplying 1 over m factors of b. Rewriting this expression in a compact exponential form, we get a to the mth over b to the mth. Implicit in writing 1 over b quantity to the mth as 1 over m factors of b is the fact that 1 to any power is equal to 1. As an example, 3 over 5 quantity cubed is equal to 3 cubed over 5 cubed, or 27 over 125. More generally, p over q quantity to the fourth is equal to p to the fourth over q to the fourth, provided that q is not equal to 0. To divide two exponential expressions that have the same base, use the common base and subtract the exponent of the denominator from the exponent of the numerator. In symbols, if x is a non-zero integer and m and n are natural numbers with m larger than n, x to the mth power divided by x to the nth power is equal to x to the m minus nth power. 3 to the 5th divided by 3 squared is equal to 3 times 3 times 3 times 3 times 3 over 3 times 3. We can cancel 2 3's each from both the numerator and denominator, leaving us with 3 times 3 times 3, or 3 cubed, in the numerator, which is the same as 3 to the 5 minus 2. Similarly, if we divide q to the 10th by q to the 4th, provided that q is not equal to 0, we can cancel 4 q's in the denominator with 4 q's in the numerator, leaving 6 factors of q in the numerator, which is q to the 6th, or q to the 10 minus 4. In the quotient rule for exponents, if the exponents of the numerator and denominator are the same, then the value of the quotient is always 1, because the same number of factors of the same base will completely cancel. The value of the exponent in the numerator and denominator is the same, so when we apply the quotient rule, we get x to the m minus m, or x to the 0th power. Since we already saw that x to the m over x to the m is equal to 1, provided that x is not equal to 0, that means x to the 0th power is also equal to 1, provided that x is not equal to 0. So any non-zero number, 5, 1,000,000, negative 3/10, or quantity 3x to the 6th raised to the 0th power is equal to 1, provided that the base is not equal to 0. In the quotient rule for exponents, we stated that the rule is valid provided that m is greater than n. What would happen if m is less than n? Take, for example, x cubed divided by x to the 7th. Expanding, we have x times x over 7 factors of x. The 3 x's in the numerator cancel with 3 x's in the denominator, leaving 1 in the numerator and x to the 4th in the denominator. Applying the quotient rule for exponents at the beginning, we would have x to the 3 minus 7, or x to the negative 4th. In order for the rules to be consistent, x to the negative 4th has to be equal to 1 over x to the 4th. Now that we have rules for 0 and negative exponents, we can say that the quotient rule for exponents is valid when m and n are any integers. Generally, we can say that if m is any integer and a is any non-zero number, then a to the negative mth power is equal to 1 over x to the mth. So 3 to the negative 3rd power is equal to 1 over 3 to the 3rd, or 1 over 27. And negative 2 quantity to the negative 3 is equal to 1 over negative 2 quantity to the 3rd power. Since we have a negative base and an odd exponent, the value will be negative, and the result is negative 1 over 2 to the 3rd, or negative 1 over 8. In practice, if we have a fraction raised to a negative exponent, it is easiest to just flip the fraction, write its reciprocal, then raise that flipped fraction to the positive of the exponent. For example, 3 over 4 quantity to the negative 3rd is equal to 4 over 3 quantity to the 3rd, which is 4 cubed over 3 cubed, or 64 over 27. Let's see if this rule for negative exponents is consistent with the other rules. If we have x to the 3rd times x to the negative 3rd, by definition this is x to the 3rd times 1 over x to the 3rd, or x to the 3rd over x to the 3rd, which is 1. By the product rule, we would get x to the 3 plus negative 3, or x to the 0, which is 1, according to the rule for 0 exponents. These arguments could be used for an exponent that is any integer, so the negative exponent rule is consistent with the other rules. Raising a base to a negative exponent is the same as raising the reciprocal of the base to the positive of that exponent. So what if we write the reciprocal of x to that negative exponent? Since x to the negative nth is equal to the reciprocal of x to the nth, the reciprocal of x to the negative nth is equal to the reciprocal of x to the nth. We know from arithmetic that fractions like these are called complex fractions, and that we can simplify them by multiplying the numerator fraction by the reciprocal of the denominator fraction. So we get 1 times x to the nth over 1, or just x to the nth. Similarly, if we have a base raised to a negative exponent divided by another base to a different negative exponent, we can just flip the bases and rewrite them with positive exponents, provided that neither base is equal to 0. Let's look at an example that uses a combination of rules. We have a fraction with 3a squared b to the negative 1 in the numerator, and 3 cubed a to the negative 1 b cubed in the denominator, all raised to the negative 2. First, let's rewrite the entire base fraction as products of factors with the same base. And we get 3 over 3 cubed times a squared over a to the negative 1 times b to the negative 1 over b cubed, all raised to the negative 2. Using the product rule to simplify each factor, we get 3 to the 1 minus 3 times a to the 2 minus negative 1 times b to the negative 1 minus 3, all raised to the negative 2, which simplifies to 3 to the negative 2 times a cubed b to the negative 4, all raised to the negative 2. Applying the definition of negative exponents within the parentheses, we get 1 over 3 squared times a cubed times 1 over b to the 4th, all raised to the negative 2, which simplifies to a cubed over 9b to the 4th, all raised to the negative 2, or 9b to the 4th over a cubed, quantity squared. Applying the negative exponent rule to the exponent outside of the parentheses. Using the power of a quotient rule, we get 9 squared times b to the 4th squared over a cubed squared, which simplifies to 81b to the 8th over a to the 6th, using the power rule for exponents. In this Anicast, we looked at all of the basic rules of exponents: the product rule for exponents, the power rule for exponents, the power of a product rule, the power of a quotient rule, the quotient rule for exponents, the zero exponent rule, and the negative exponent rule with its variations. All of these rules involve exponents that are integers. In future Anicasts, we will look at rules of exponents involving exponents that are rational and real numbers.